Hi guys, it's your guy Olumide, and today we're gonna be solving another one of the most commonly asked tech interview question. It's the median of an integer string. It's a high rank question that is asked by top tech companies including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. The problem statement states that design a data structure that supports adding integers from a data stream and retrieving the median of all elements received at any point. So it's a data structure that we're trying to design now, and it will have two major methods or functions. The add method to add an integer to the data structure, and then the get median method that return the median of all integers so far. So those two things are what will comprise the data structure, and as we can see in this example, add method is called on the data structure, and we're trying to add an integer 3, then we add an integer 6, and adding an integer 3 now, the data structure now contain let's say a list of 3. Let's just use the list as an analogy, and adding the 6, integer 6, now the data structure contains 3,6 when sorted, because the problem and the examples or the integers will not be added in an ascending order. Any integer can be added, so that's why they place when sorted there. So because it might not necessarily be sorted when providing these values. So get median is called now, and median is 3 plus 6 divided by 2, because we have 3 and 6 in the data structure, so the median becomes 4.5. So don't forget one thing about median, that median is not just calculated over a series of numbers or a set of numbers. So the number has to be sorted before we can correctly calculate the median, right? So we perform another add method. So this means that we can perform add and get median at any point in time. So performing another add and adding one to the list now. So even though one is added last, but okay, this is the data structure after it was sorted, 136, and when we call the get median at this point in time, the median is 3, because the length of the data structure is now 3, and then the middle element is the 3.0, and so this is what the problem statement is trying to provide us with. Now we know that the median is always found in the middle of a sorted list of value. The challenge with this problem is that it is unclear on how to keep the values in the data structure sorted as new values arrives, since it is not necessarily stated that this value will come in the in a sorted manner. So as we can see, even in this explanation here, we see that 3 comes before 6 and then 1 comes eventually. So the challenge is, how do we keep this value sorted so that we can get the correct median? Now one important point to recognize is that we don't necessarily care if all the values are sorted. We don't necessarily care if all the values are sorted in the data structure. One thing that we need is that the median value is sorted. So now we don't know, we can have a long list of data and values in the data structure or in the integer stream now, so we don't really want to bother about the all extreme numbers in their sorted form, but we just want to ensure that the middle is sorted. Just like in this case, if the middle can be sorted right here, then we can know that the median is 3.0. But is it possible to actually position this value in the middle without necessarily sorting the all values? Is it even possible that we get the median value, be it 3 and 6 in this case whereby it is even, or be it only 3 in the case whereby it is odd here? Is it possible to get it sorted, just the median value, without necessarily sorting the whole data structure? Let's consider these elements right here that contains an even number of values that are arranged in sorted order. We see that there are two median value here because they are arranged in sorted order now. So these are the two median value 3 and 4. And these two values are what we need to calculate the median of this particular set of elements. When a list or a data structure contains two median value, we can make the following. We can see the following observation. The first median is the largest value in the left half of the sorted integers. Right now, we said this particular list of elements is even because it contains even number of elements, meaning that we can divide this set of elements into two halves. This is the first half here, and this is the second half right here. So the first median is the largest value in the left half. Look at the left half. We will see that because it is sorted, then the left median or the first median is actually the largest value in this left half of the sorted integer, while the right median, we can see that it is the smallest value in the right half of the sorted integer. So we have these two observations. Now you will observe that if we find a way to split this data into two halves, with the first half containing the smaller values and the second half containing the larger values, we will just need an efficient method to identify the largest value in the smaller half and the smallest value in the larger half, because now we divide this whole data into two halves, and the left half is always, every element in the left half is smaller than every element in the left and right half. So to find the median, we just need an efficient method that will get us the largest element in the smaller half, which is the left half, and the smallest element in the larger half, which will give us 3 and 4, and from there we can efficiently get the median of the data structure. Now this is where Heaps comes in, the Heaps data structure. We can use a combination of minimum heap and a maximum heap. Two heaps data structure now, a minimum heap and a maximum heap, where the maximum heap will help us to manage the left half, so keeping track of the top value, so which will represent the first median value. So when the maximum heap keep track of the left half, it will help us to place the maximum value at the left half at the top of the heap, so you can easily access it. So, and that maximum value, that value at the top of the maximum heap will be the first median value, while the minimum heap will help us to keep track of the right half, so to keep track of the minimum value in the right half, so where the top value will represent the second median value. Whereas if the total number of elements is odd, don't forget that in this case the total number of elements is even here, and that's how we're having two median values. But if the total number of elements is odd, we will only be having one median value, and in this case we just need to use one of the two heaps to store the median value, and we can decide to use the maximum heap to store it. So it's gonna be stored in the left heap, which is the maximum heap. Now before we populate the heap, we need to understand the behavior that each of these heap, the maximum and the minimum heap, will follow. The first condition is that all value in the left half, which means the maximum heap, must be less than or equals to all value in the right half, which is the minimum heap. And what I'm trying to talk about is that after dividing it into two halves now, every value 0, 1, 2, 2, 3 must be less than every value in that left half must be less than every value in the right half, because that means it is sorted. So 4, 5, 6, 7, 8, 9. Another thing is that the two halves should contain an equal number of values, except when the total number of values is odd. So what they're trying to tell us is that, look at the case of this median of this even number of elements now, the left half and the right half must contain even number of value, right? So but in a situation whereby the length of the elements is odd, or the number of elements is odd, just like in this odd element now, the left half must use at most be one element higher than the right half, what we're trying to say is that because it is odd, so it has to be at most one element. So is either they are equal or it is at most one element greater than the right half, not up to 2. So in a more coded manner, what we're trying to say is that the maximum value of the maximum heap, we have the maximum heap which represents the left half. So now it must be less than or equals to the minimum value of the minimum heap. Why? Because we know that a maximum heap is going to keep the maximum value at the top of the heap, and definitely every value that is inside the heap will be less than or equals to that maximum value. So therefore that maximum value must be less than or equals to the minimum value in the minimum heap, which is the right half. So that will ensure that it is sorted. Just like in this case now, we say that the maximum value in the maximum heap here is 3, in the left half is 3, while the minimum value here is 4. So we have to ensure that 3 is always less than 4. That is the maximum value here, it is less than minimum value, so that that is a way to make sure that it is ordered. The left half must always be less than the right half. So another the other condition is just trying to tell us that the heap should be of equal size, but the maximum heap can now have one more element than the minimum heap in a situation whereby it is odd. So they contain odd number of elements. So the maximum heap can just be one more element greater than the minimum heap. Let us consider these examples here. The maximum heap in the left half and the minimum heap in the right half. Let's consider this example to explain what we have been talking about right here. So now we want to add a number or a value 3 into either the maximum. Don't forget that this maximum heap and the minimum heap too is just a whole set of integer stream that is divided into two halves, the left half and the right half. So now to decide where the number 3 is going to go into, fine, this maximum heap, now the first law tells us that the maximum value of the maximum heap must be less than or equals to the minimum value of this minimum heap. So when we want to add a number 3, we can't add it to this maximum heap. Why? Because even the top value of the minimum of this maximum heap here, the top value is 4, and 4 is greater than 3. So we're gonna add it to the maximum heap because it falls under 3. Yes, and if the maximum value of this left half can be greater than 3, definitely it belongs to 3, because every other thing that is in this right half will always be greater than 3, and that's why we have 5, 7, 8, 9. So it belongs to 3. So what we do is that we add it into 3, but adding it into 3 does not guarantee that it's going to be at the top element, because it's not even up to the topmost elements in the top of the heap. So it's just going to be inside the maximum heap. So but now we say that the size actually is 5, and is actually 5 now, and the size of this right half is 4. So I'm using this example because right from time this example has satisfied this condition that is here, which says that 4 must be less than 5, which means the maximum element in this maximum heap must be less than the minimum element in this one, right? So and also the size is 5 to 4. The size of this maximum heap is 5, while the size of this minimum heap is 4, which is still correct, because this means that the total is 9, and 9 is odd. So the maximum heap is going to have one more greater than the minimum heap. But right now we added 3 to this maximum heap, right? So and the size is now 6, while the size of this minimum heap is 4. That is, the size of the other right half is 4. So 6 is 2 greater than 4, and that is more than 1. But the condition here tells us that the heap should be of equal size, but the maximum heap can have one more element greater than the minimum. So it is now 2 more elements greater than it. So it has defied the condition that we stated. So one have to move on to the right half so that they will maintain a 5-5 order. So it must not be more than 1. The left half must not be more than 1 greater than the right half, and that is even for a situation whereby the length of the element are odd. If the length of the element are even, then they should definitely be of the same length. Consider now this time 6 plus 4 gives us 10, right, which is even length, so there should be 5 5, not 6 4. So what we want to do now is that we want to move the topmost element, that is the element at the top of this maximum heap. We want to move it to the minimum heap, because that is the element that is greater, that is the largest element in this minimum heap. So I'm moving it right here. So, and that's what we have at this point. You see, we move 4 from here to here, so 3 will now take the maximum element in this maximum heap now, while 4 will take the smallest element in this minimum heap. So, and that way they maintain the size of 5 to 5. So this is how this is what it means. So this way now, if we want to find the median, we just need to get, because the length is 10, right? The length of this one is 10, of the total left half plus right half is 10. So we just have to take the top of this maximum heap and the top of this minimum heap. So the median will be 3 plus 4 divided by 2. That is the median of this particular array. So again, to ensure that the size of the heap does not violate the condition that we placed there, that the heap should be of equal size, or the maximum heap should be only one more element greater than the minimum heap, even if they are not of the same size, the maximum heap should not be more than one greater than the minimum heap. And to ensure that, what we do is that after adding an element to the heap, just like I explained there, whereby we added 3 to this maximum heap now, and after doing that, we need to check if the left half heap size exceeds the right half heap size by more than 1. If we do, we need to rebalance the heap by transferring the left half top element to the right half. So this, because now this is the left half now, right, and this is the right half here too. So now, because the left half is now more than 1 greater than the right half, look, the left half is 2 greater than the right half. So what we do is that we need to balance it by moving the top of this left half to this right half. This is the top of the maximum heap, so to this right half, which is the minimum heap. So that way it will become balanced. So because it is balanced, because now it is not more than 1 greater, the left half is not more than 1 greater than the right half now. So, and the second condition is that, okay, what if it is the right half heap size that exceeds the left half heap size? So don't forget that the left half size must not be more than 1 greater than the right half size, right? But the right half size must not even be greater than the left half size at all, because in a situation whereby the data structure or the number of elements is even, they are meant to be equal, just like this, balanced. But in a situation whereby it is odd, there will be one more to the left than to the right. That's why we place the condition that the left must not be more than 1 greater than the right, but the right is not even supposed to be greater than the left at all. So in a situation whereby the right half side is greater than the left half, we really need to shift it toward this side so that they will maintain the balance. So in a situation whereby the left half is right half is greater, what we do is that we are gonna shift it toward this side until they maintain the balance. So, and that way it is balanced now. So it's just like the right half is 6, the left half is 5. So we really need to merge it together so that right half become the right half, left half become 6, while the right half become 5. That is still better, so than the right half being 6 and the left half being 5. That's a problem. There will be a problem there. So and in a situation like that, we are just gonna move it to balance it. Now whenever we are now asked to return the median, to find the median using the method get median, we are gonna check if the total number of elements is even. So if it is even, then both median value can be found from the top of each heap. So why? Because we know that the left heap will hold the top of the left heap will be the maximum value, while the top of the to the left array or to the left half, while the top of the right of the minimum heap, which means the right half will be the minimum value. So those two values are actually the median value that we need. That is in a situation whereby the number of elements are even. But in a situation whereby the number of elements is odd, don't forget that in a situation like that, the left half will have one more element higher than the right half, and that particular element at the top of the left half is actually what will be the median value. And that's how we go about solving this problem. You're gonna understand even more in the code implementation. Now let's move on with the code implementation now. For the median of an integer stream, so we're going to be creating a class called the median integer stream. So don't forget the problem statement specify that we have some method like the add method, the get median method, and we can do that with a class. So to make it more understanding, I'm gonna create an instance, and so we know what we are really gonna be working on. So this is the instance of the median integer stream, and want to be able to perform an add operation or functionality or method that we add a number to the integer stream and could add another number 6, just like our problem statement specified, and then we can perform a get median at any point in time, and then perform another add and get another median. So now that we have a clue about what our median integer stream is really going to be doing, let's move on to implementing the initialization now. So in this initialization, we'll be passing in self, the instance itself, and then we want to be passing in, that's all. So we want to be creating some value here, the right half and the left half. So don't forget that this is an integer stream, and it's gonna be taking in a series of numbers, just like what we are performing here. We are trying to add 3, 6 and any other number, so we really need to have our left half of these streams and our right half. So it is going to be a heap, so a minimum and maximum heap, where the left half is going to represent the maximum heap because it's going to be holding the we want the maximum number from the left half, so that's why we're using a maximum heap. And our right half, now we are using a minimum heap. So alright, now really, this time we're using two different heaps now, the maximum and the minimum heap, but Python actually supports basically one heap, which is the minimum heap. So whenever you create a heap data structure now using the import heap, let's import our heap. So when you import heap like this using heap q, so whenever you do this import heap and you're trying to pass in numbers, so numbers like 3, 6 into the heap, it will prioritize and place the smallest number at the top of the heap. So meaning that in this set of 3 and 6 now, 3 will be at the top of the heap by default basically. So but now we need two functionality of heap, the minimum and the maximum heap, but Python guarantees only one, which is the minimum heap. So in order to form the maximum heap, what we're going to be doing is that in a case whereby we put in 3, we're going to put in -3 instead. When we have -3 and -6, so for a minimum heap which Python allows and supports, -6 is going to be at the top because it is lesser than -3. So that way now we will be able to implement the maximum heap, will I say maliciously. So really, if we just put in 3 and 6, 3 will be at the top. But now if we want to find the maximum heap of this same 3 and 6, 3 and 6 with 3 being at the top, that's minimum heap because 3 is less than 6 and it is at the top. But if we want to implement maximum heap, what we're going to be doing is that we're going to be using -3 and -6 instead. So when we put -3 and -6 is going to be at the top. So when we are trying to retrieve an element from a maximum heap, which means that the left half, we are going to be putting it inside as a negative, and when we are collecting it, we multiply it by -1 so that we can get the number. So that is just a way to implement the maximum heap in another way, because normally if we put in 3 and 6, 3 will be at the top of the heap because Python is minimum heap by default. It supports minimum heap by default. So to make it support maximum heap, we're going to be putting in the negative for the maximum heap. So and why I'm saying this is because we'll be needing to heap. The left half will be using the maximum heap, and the right half will be using the minimum heap. So that being said, let's define the add method now to add a number. So the number is going to be an integer, and the return of the add number will be a none, because we are actually do not need any return. We just want to add to the stream. So and what we want to do is that we want to check if self dot left half. Don't forget, self dot left half represents the left half, which is the maximum heap. So if not self dot left half, I'm going to explain, or self or num is less than or equals to minus self dot left half of 0. So what we're trying to do here is that in a situation whereby the left half, which is this maximum heap, in a situation whereby it is empty, we really just want to do that thing. That is anything we're gonna be putting here now. We want to do it based on the fact that if the left half is empty, and what we want to do really is that we want to add a number. So if the left half is empty, that means that nothing has been added to the left half and to the right half, just like now that is still empty. We want to add it on that first go. So or in a situation whereby the number we are trying to add is less than or equals to minus self dot left half. Don't forget that I told you that our left half is representing the maximum heap. So we are using negative so that minus 10 is lesser than minus 6. So minus 10 will be at the top, because we need the higher number to be at the top for maximum heap. So in a situation like that, whereby num is less than the number we are trying to add into the integer stream is less than the top of the number at the top of the maximum heap, definitely we need to insert it at that same maximum heap. If you go back to the logic that I explained, you understand why we need to insert it at that same maximum heap is because every number in that maximum heap, even including the number at the top of the heap, is lesser than or equals to every number in the right half, which is the minimum heap, because it is ordered. You understand? It is sort of ordered. So if a number now that we're trying to add fall below the top of the maximum heap, that is, if it is lesser than the number at the top of the maximum heap, definitely we have to push it to the maximum heap, that is to the left half. So and that's what we're gonna be doing now. So we'll be doing heap q dot heap push, and we'll be pushing to this left half, and what we want to push is minus num. Don't forget the left half is actually a maximum heap, so we are going to be pushing in minus num so that it could behave like that. So after doing this, now I want to check so that it could behave like that. What I mean is that pushing it into the maximum heap now is going to ensure that because Python is minimum heap by default, so when we negate the number, a number that is 10 when negated will become minus 10, which means it's the smallest now. So that's what I'm trying to do there. So that means that the smallest will still be at the top, so minus 10 will be at the top as if it is the minimum, whereas we know that we intentionally negate it. It is the maximum, but we intentionally negate it because we want to have this maximum heap nature. Okay, now after putting it there, we want to now check if the length of this self dot left half, if the length is actually greater than the length of the right half. So plus 1. So what this one is trying to say, don't forget that the left half can be at most 1 greater than the right half. It must not be more than 1. So if it is now more than 1, what this one means is that fine, the left half might be greater than the right half, but if it is even now greater than right half plus 1, that is now up to right half plus 2 upward, then it's too much, and we need to really perform something, a heap push into the self dot right half comma heap q dot heap pop self dot left half. So yeah, so what we do there is that because the left half is now is greater than right half plus 1, that is 2 times or more greater than the right half, so we pop out of the left half and we push it into the right half, so ensuring that the top element in the left half is now moved to the right half. So that's it. So but in a situation whereby that's all we want for that. But in a situation whereby this is not actually the first element, in a situation whereby the left half is not empty, and because we use all here, so in that situation, in a situation whereby the number is actually greater than the topmost element in the left half, we want to add it to the right half then, because now it qualifies to be in the right half. If it is greater than the maximum number in the left half, definitely we want to put it in the right half. So what we do is that we can perform an heap q dot heap push. We are trying to push it into self dot right half now, comma num. If you notice, we are not pushing minus num now, because right half wants it to behave normally like a minimum heap, so we are not adding minus num, unlike here where we add minus num. So after doing that, now again we are going to check if the length of self dot left half, if it is greater than if it is less than the length of the self dot right half now. So in a situation whereby it is greater, be it by 1, we really need to make it balanced, because the right half must not be greater than the left half. So it has to be at most equal to it. The left half can be greater than the right half by 1, but the right half must not be greater than the left half. So because of that, we are gonna push a q dot heap push, so into the left half, from the right half to the left half. Self dot left half comma heap q dot heap pop self dot self dot right half now. So we are popping out of the right half into the left half, so in that situation. So and that's just what we want to do here. So that's it. That's how we add a number into the integer stream. So let's define the get median method. The get median method now, so it will just take in self. It's gonna, and what we want to do is I want to check if self dot, if the length are equal, if the length of self dot left half, if it's equals to the length of self dot right half. And what this means actually is that, what this means is that if they have the same length, definitely imagine 2 plus 2, maybe the length is 2 in both cases, or 5 plus 5, or 10 plus 10, or 7 plus 7, is always going to give us an even length, and that means that it is even. So we're going to be returning self dot left half of 0, so the top element in self dot left half plus the top element in right half of 0, so divided by 2. That's what we'll be returning. But don't forget, we have to put a minus here, because when we are adding this number into the left half, we added minus. Look here, right here we added minus, to mimic the maximum heap behavior. So we have to add minus again so that it will convert it to the real number. So the 10 that we added as minus 10, when it's coming outside, we add minus again to make it 10 back. So but in a situation now whereby they are not equal, probably that means that the left half is greater than the right half by 1, so it is odd. So what we're going to return is self dot left half of 0. So mean that the top elements in the left half, that's definitely going to be the median, because when the left half is greater than the right half by 1, then definitely the median values are the top element of that, at the top of the heap of that left half heap, that is the maximum heap. We are adding minus again because we have to convert it to the real number. So, and when we run this code, that's just it actually. So let's run the code and see what's going to be returned. So we'll be expecting two numbers, one for this print median after adding 3 and 6, while the other for adding the other will be for adding 1 again. So we see 4.5 and 3, which is correct because 3 plus 6 gives us 9, right? And 9 divided by 2, because it's just two numbers that we added now, so it's an even number. So 3 plus 6 gives us 9. 9 divided by 2 gives us 4.5. But when we added 1 now, the data structure becomes 1, 3 and 6. So the median becomes 3, as we can see here. So that's how to solve this problem. And I hope you understand this. So I'm Olumide by name. Do well to like, comment, share, subscribe to my YouTube channel, and follow for more problem solving like this. Thank you.